All right, we're going to move into Chapter 5 and begin talking about rigid bodies. And we're going to start here with rigid body equilibrium. So suppose we have forces here. And free moments. Or a couple moments. Draw a moment here. Maybe another one here. So using the methods from previous chapters, the force couple moment system here can be reduced to just a simple reaction moment about some point O. Let's just pick a random point here, O, and a reaction force. So all these forces, and we'll get a reaction force, and we can get also a reaction moment. And we can do this about O. Now, if the reaction moment about O equals 0, and the reaction force, let's get some, equals 0, then our body is in equilibrium. So in summary, the reaction force equals the sum of all forces, and if this equals 0, and if our reaction moment equals the sum of all moments, say about O, and that equals 0, this is all that is necessary to be in equilibrium, necessary and sufficient. Further, we can recognize that this means that your sum of your forces in your x direction equals 0, the sum of your forces in your y direction equals 0, and the sum of your forces in your z direction equals 0. Likewise, it means the sum of your moments in the x direction equals 0, sum of your moments y direction equals 0, and the sum of your moments z direction equals 0. Okay, let's talk about some supports. So let's have a support. Set up a table here. The reaction we get from it, and the number of unknowns associated with it. So our first support is just a roller. So it might be on the end of the beam, like so. We can also represent this, you might see it represented with multiple wheels. You might see it represented as a wheel in constrained so that it can't move in the y direction. And that's what's assumed here too. You're not getting any movement in the y direction. Also could be represented by a rocker, or just a member touching the ground. In all these cases, there is no friction on the surface that is rolling. We would model this in a free body diagram as a reaction, say R as our force, and it leads to one unknown. So this is a roller. We can have a pin that is a little similar, but not exactly the same, because a pin is constrained, attached to the ground, and a pin might look like this. The reaction we end up getting is, let's do this coming in at an angle so I can draw two here. So we're going to get one of two things. We can represent this like this with a simple reaction, but we also have an unknown direction, alpha. Or we can represent it like this, where we have two forces, an Rx and an Ry. So this is kind of broke down into two forces then. This has two unknowns, brings two unknowns. And then finally, we'll have fixed. So a fixed is completely secured. Think of a pole like this, where this is our ground, completely secured. In this situation, we have, again, one of two ways of looking at this. We're going to have a reaction with an unknown angle, but in addition, we also have a moment. We can represent that with two forces like we did above, and a moment. So either way, in this case, you're going to have three unknowns. So those are the basic supports that we're going to have. We can also have other things, like we can have a rope, or a chain, or it could be a link, like so. In which case, we will have a reaction that is in the direction along the line of axis of the rope or the link. Like so. And that'll just be one unknown. So those are some supports. So now let's talk a little bit about sketching our free body diagrams of rigid bodies. So let's imagine we have an engine say we have some chains here that we've attached to hold this engine up. There'll be forces associated with those. And then the engine has a center of gravity, and we can just represent our weight at the center of gravity. That accounts for all the internal forces, the distribution of forces between these mounting points, and internally all the screws and the nuts with equal and opposite forces and moments, so that we only have to represent this whole thing as a weight centered at the center of gravity. And that's if we have weight. So we'll apply our weight at the center of gravity while we're doing our free body diagrams. Let's look at some examples with maybe a beam. Say we have this beam that is secured to the wall like so, and it has maybe a force on it. Newtons. And this is applied, let's move this over, applied closer to the wall. Newtons. And we're talking maybe like 2 meters from the wall. This whole thing maybe is 6 meters long. Well, we can set up a free body diagram here for this, where we look at just our beam. And let's put all the forces on it that affect it. So, of course, we're going to have this 1200 Newton load. And say our beam weighs, it would be given in the problem if it was going to be an issue, but say it weighs 981 newtons. We'll put that in the center of gravity on the beam, so that's going to be dead center in the beam. Over here. So an assumption we'll make really is that this is applied at the center of the beam, even though it's drawn on the top of the beam. Alright, now since this is a wall support, we're going to have some reactions to keep this whole thing in equilibrium. This will be a fixed reaction. So what we're going to end up with is we'll end up with a force in the y direction. Let's call it a reaction, R. Reaction in the y direction, a reaction in the x direction, and we'll have a moment here. It doesn't matter if I draw that moment in the correct direction, because when we do our analysis, if I drew it incorrectly, it will come out being a negative number. So this was 3 meters, and this was 2 meters. Got to put some dimensions on here. 3 meters because it's half the distance of the beam. Okay,